Welcome to this lesson on controls in scientific research. Today we're going to explore why every serious experiment needs at least one proper control, and what happens when controls are missing. Let's start with the fundamental question. What exactly is a control in an experiment? A control is essentially a standard of comparison. It's a condition in your experiment that allows you to determine whether your independent variable actually caused the effect you observed. Without proper controls, you cannot determine causation. You might see an effect, but you won't know if your treatment caused it or if something else did. Let me give you a concrete example. Imagine you're testing a new headache medication. You give 100 people with headaches this new pill, and after 30 minutes, 75 of them report feeling better. So 75% of people felt better after taking the pill. Does this prove the pill works? This is the critical question. Can we conclude that the pill caused the improvement? The answer is absolutely not. Here's why. Many headaches go away on their own within 30 minutes. Maybe 60% of headaches naturally resolve in that time. We have no way of knowing without a control. There's also the placebo effect. People often feel better just because they believe they took medicine, even if it's a sugar pill. This is a well-documented psychological phenomenon. Without a control group, we cannot separate the drug's actual effect from natural recovery and the placebo effect. This is why controls are absolutely essential. Now let's discuss different types of controls. The first and most common is the negative control, also called a blank control. A negative control receives no treatment, or receives an inert treatment that should have no effect. This establishes your baseline. In our headache example, the negative control group would receive a placebo pill that looks identical to the real pill, but contains no active ingredient. Both groups should be otherwise identical. Now let's say the treatment group has 75% improvement, but the control group has 60% improvement. What does this tell us? The actual treatment effect is 75% minus 60%, which equals 15%. So the drug only provides an additional 15% improvement beyond natural recovery and placebo. This 15% represents the true pharmacological effect of the drug. Without the control, we would have incorrectly attributed all 75% to the drug. The second type is a positive control. This is a treatment known to produce a specific effect. A positive control uses a treatment that is already known to work. This verifies that your experimental system is capable of detecting an effect. For example, if you're testing a new antibiotic against bacteria, you might include a positive control using a well-established antibiotic like penicillin. This confirms your bacteria can be killed and your methods work. Here's how all three groups compare. The new drug is your experimental group, the positive control should definitely work, and the negative control should show minimal effect. Here's why positive controls matter. If your positive control doesn't work, something is wrong with your experimental setup. Maybe the bacteria were already dead, or your measurement technique is faulty. If the positive control fails, the entire experiment is invalid. You cannot trust any of your results because the system wasn't working properly. Type 3 is a reference control, also called a standard control. This is used when you're comparing your treatment to the current standard treatment. A reference control represents the current best available treatment. This is especially important in medical research, where you need to show your new treatment is better than what's currently used. For example, if you're testing a new chemotherapy drug, your reference control would be the standard chemotherapy currently prescribed. You need to prove your new drug is at least as good, or preferably better. Type 4 is a no treatment control, which is subtly different from a negative control. In a no treatment control, the subjects receive absolutely nothing. No pills, no injections, no procedures. This is different from a placebo, where subjects still receive something, even if it's inert. This type of control helps separate the placebo effect from the effect of simply doing something. Sometimes the act of taking a pill or receiving attention from medical staff has its own effect. Let me give you a detailed, real-world example involving plant growth. Suppose we want to test whether a new fertilizer increases plant growth. We set up three groups. Group A gets the new fertilizer, Group B gets water only as a negative control, and Group C gets nothing as a no treatment control. Everything else must be identical. After 30 days, we measure plant height in centimeters. Let's say we get the following results. Group A with fertilizer grew to 25 centimeters. Group B with water only grew to 18 centimeters. Group C with nothing grew to 12 centimeters. Now here's the question. What is the true effect of the fertilizer? Can we just say it's 15 centimeters because that's how much Group A grew? No! We need to account for natural growth. Group C grew 2 centimeters with no intervention at all. This represents natural growth from stored nutrients in the seed. The effect of water alone is 18 minus 12, which equals 6 centimeters. This shows water itself contributes significantly to growth. The true fertilizer effect is 25 minus 18, which equals 7 centimeters. This is the additional growth beyond what water alone provides. Notice how crucial the controls are here. Without Group B, we couldn't separate the fertilizer effect from the water effect. Without Group C, we couldn't account for natural growth. Now let's talk about what happens when experiments lack proper controls. This is where bad science happens. Here's a classic example. An early study claimed that coffee consumption was linked to heart disease. Researchers found that people who drank more coffee had higher rates of heart attacks. The problem was they didn't control for smoking. It turned out that heavy coffee drinkers in that era were also much more likely to be heavy smokers. Smoking causes heart disease, not coffee. Coffee consumption was correlated with heart disease, but it wasn't causal. The real causative factor was smoking. This is a confounding variable. This diagram shows the relationship. Coffee and smoking overlap, but smoking is the true cause of heart disease. Coffee was just associated because smokers drank more coffee. We also need to discuss statistical significance versus practical significance. Even with proper controls, we must interpret results carefully. In science, we typically use a p-value less than 0.05 as the threshold for statistical significance. This means less than 5% probability the result occurred by chance. However, statistical significance doesn't mean the result is practically important. With a large enough sample size, even tiny effects become statistically significant. For example, imagine a blood pressure medication that lowers pressure by 1 millimeter of mercury compared to a placebo control. With 10,000 subjects, this might be statistically significant. But an effect size of 1 millimeter of mercury is clinically meaningless. It won't improve patient outcomes despite being statistically significant. Another critical point is that controls must be properly matched to your experimental group. They should be identical except for the independent variable. Let's say you're testing whether a learning app improves math scores for children. You give the app to 5th graders and compare their scores to 3rd graders who don't use the app. This is terrible experimental design. 5th graders naturally perform better than 3rd graders regardless of the app. Age is a massive confounding variable. The proper control would be other 5th graders who don't use the app. Everything should be matched. Age, school, teacher quality, prior math ability. Only the app should differ. This brings us to randomization, which works hand in hand with controls. Randomization helps eliminate selection bias. When you randomly assign subjects to treatment or control groups, you distribute unknown confounding factors evenly across both groups. This strengthens your causal claims. In a drug trial, you might randomly assign 500 patients to receive the drug and 500 to receive a placebo. Random assignment ensures that factors like genetics, diet, and lifestyle are roughly equal in both groups. With 500 subjects in each group, random assignment becomes very powerful at balancing out individual differences. We also need to discuss blinding, which enhances the validity of your controls. Blinding means subjects don't know which group they're in. In a single blind study, subjects don't know whether they receive the treatment or the control. This eliminates bias from subjects' expectations. In a double-blind study, neither the subjects nor the researchers collecting data know who's in which group. This eliminates bias from both sides. Double blinding is crucial because researchers can unconsciously influence results. If they know who got the real drug, they might interpret ambiguous symptoms more favorably for the treatment group. Sometimes you need multiple control groups to rule out different alternative explanations. This is especially true in complex experiments. Suppose you're testing a new teaching method that involves students working in groups with computers. You need multiple controls to isolate what's actually helping. You need 4 groups. Treatment has groups and computers. Control 1 has groups without computers to test if collaboration alone helps. Control 2 has computers without groups to test if technology alone helps. Control 3 is traditional teaching. Only by having all these controls can you determine whether it's the group work, the computers, or the combination that produces the effect. Let's discuss sample size. Because even with perfect controls, insufficient sample size can ruin your experiment. Statistical power is 1 minus beta, where beta is the probability of a type 2 error. Power is the probability of detecting a real effect when it exists. Larger sample sizes increase your power to detect real effects. With too few subjects, you might miss a genuine treatment effect simply due to random variation. The required sample size n depends on your desired significance level alpha, desired power, which relates to beta, the variance sigma squared, and the effect size delta squared. As a rough rule of thumb, you want at least 30 subjects per group for the central limit theorem to apply. But more is always better, especially if you expect a small effect size. Let me give you a real-world consequence of proper controls. In vaccine trials, having the right controls literally saves lives. Phase 3 vaccine trials often involve 30,000 or more participants. Half receive the vaccine, half receive a placebo. This large sample size is necessary to detect rare side effects. The COVID-19 vaccine trials used about 40,000 participants. They needed this many because they had to detect not just efficacy, but also rare adverse events that might occur in only 1 in 10,000 people. Vaccine efficacy is calculated as C minus T divided by C times 100%, where C is the number of cases in the control group and T is the number in the treatment group. Without placebo controls, you cannot calculate efficacy. You wouldn't know how many infections would have occurred naturally without the vaccine. Sometimes researchers use historical controls, comparing current treatment to past data. This is generally considered weak evidence. A historical control uses data from patients treated in the past, often before the new treatment was available. You compare your current treatment group to this historical data. The problem is that many things change over time. Diagnostic criteria, patient populations, supportive care, measurement techniques. These confound your comparison. Historical controls are only acceptable when concurrent randomized controls would be unethical, such as when a treatment is clearly life-saving and withholding it would be harmful. Let me give you an analogy to help you understand controls. Think of scientific experiments like navigating a ship. Your experiment is like a ship trying to reach the true answer. Without controls, you're sailing without instruments. You might drift off course due to currents you can't see. Controls are like your compass, sextant, and maps. They tell you where you are relative to where you should be. They let you correct for invisible forces pushing you off course. Confounding variables are like ocean currents. You can't see them directly, but they push your ship in the wrong direction. Without controls, you'll end up somewhere completely different from your intended destination. Let me highlight some common mistakes researchers make when designing controls. Mistake 1. Having drastically unequal sample sizes between treatment and control without good reason. This reduces statistical power. Mistake 2. Not controlling environmental factors. If your treatment group is tested in the morning and control group in the afternoon, fatigue becomes a confounding variable. Mistake 3. Using convenience samples for controls instead of random assignment. If volunteers choose their group, selection bias invalidates your results. Mistake 4. Changing your measurement protocols or criteria mid-experiment. This introduces systematic error that can masquerade as a treatment effect. We need to revisit effect size because it's crucial for interpreting your results even with perfect controls. Cohen's d is a common measure of effect size. It's the difference between group means mu1 minus mu2 divided by the pooled standard deviation sigma. By convention, d equals 0.2 is considered a small effect, 0.5 is medium, and 0.8 is large. However, context matters more than these arbitrary guidelines. In medicine, even a small effect size might be clinically important if it saves lives. Finally, let's discuss why even well-controlled experiments sometimes fail to replicate. In recent years, researchers have discovered that many published findings cannot be replicated. Even studies with apparent proper controls sometimes don't hold up. Why does this happen? Sometimes the original study had hidden confounds. Sometimes it was a statistical fluke. Sometimes publication bias means only positive results get published. This is why pre-registration of studies matters. By declaring your hypotheses and analysis plan before collecting data, you prevent p-hacking and selective reporting. No single study, no matter how well controlled, is definitive. Multiple independent studies with consistent results and proper controls build scientific consensus. Let me summarize the key principles we've covered today. Every serious experiment needs at least one proper control group. Without controls, you cannot establish causation. Different types of controls serve different purposes. Negative controls establish baseline. Positive controls verify your methods work. Reference controls compare to current standards. Controls must be properly matched to treatment groups in all ways except the independent variable. Random assignment helps achieve this. Blinding, especially double blinding, reduces bias from expectations and interpretation. Sample size must be large enough to detect real effects. Calculate required sample size before starting your experiment. The absence of proper controls makes it impossible to determine whether your independent variable caused the observed effect or whether something else did. This is the fundamental reason controls are essential. Remember, science is fundamentally about systematically eliminating alternative explanations. Controls are the primary tool for doing this. Without them, you're just making observations, not doing experiments.